Hi everyone, my name is Vaibhav Singh and I'm a second year PhD student at Mela in Montreal. And today we are going to build a GPT-1 from scratch and we will train it on Wikipedia dataset. As you might have already known, that there exists a similar video by none other than Andrew Karpathy, who explains in a beautiful manner how do we transition from a bigram model to GPT-1. And it's just a gold mine and a super video to watch through. It's a 2-hour video, so we'll be following and we'll be doing a very similar thing, but it will be more condensed and a much shorter video. So if anybody is interested in going extremely deep down into the details, please watch that video. It's just a delight to watch. Another thing, I'm not coding everything from memory, so I already have a reference code in front of me and I'll be just walking everything down from there. As far as I can do, I'll try to write everything from memory, but I do have a reference code. So don't feel that, oh, how is he able to write so much code without any kind of guidance. I am not Andrew Karpathy, so okay. Let's get started without any further ado. So in front of us, we have an empty GPT directory and we would be needing a model file. We would be also needing something data related stuff. So let's just name it as datautils.py. And finally, we would be needing a file to run everything and stitch everything together. So let's just call that as run.py. That's it. We won't be needing anything else. So let's start building the model file. So the first thing is that we need torch. We would be needing the module, so import torch.nn as nn, and we will see what else we would be needing down the lane. So I would like to structure my GPT model through classes. So the first class that I would need is the big model class, which is class GPT, and that would inherit nn.module. All right. It would be needing its init function and self. Okay. So what are the parameters that this GPT model needs? The first parameter is vocabulary size. So just a second. Oh, it's showing some compiler. Oh, okay, fine. So vocabulary. Oh, okay. Vocabulary size. And I'm just assigning it some 50,000. Oh, I made a mistake, sorry. Size. We would also be needing the embedding dimension or embedding size, and it will be 768 for now. Okay. Then we would be needing the sequence length, that how long, or basically what's the context size of our sequences. So sequence length, let's keep it to 512. And finally, we would be needing number of layers. Let's set to 4, or we can just have a small model with just 2 layers maybe. We can pass it on when we'll be running the model, we'll just pass these parameters. Do we need anything else? Oh yeah, since we will be implementing multi-headed attention, so we would be needing the number of heads. So number of heads, let's just say 2. All right, so that's it. Now let's call the super function GPT self dot init. All right, perfect. So now let's initialize everything. Okay, so the first thing that I need in my model is def. The first thing I need is self.embedding. Embedding, and this embedding will be handled by an object of embedding class. So let's call that as GPT embedding. We will define it later. Like we are just layering, we are just basically listing down all the components that we need, and we will define each of them iteratively. So GPT embedding, again, it needs vocabulary size, it needs the embedding size, and it needs the sequence length. Perfect. We'll define this quickly as a dummy class. Oops, sorry. Okay, class GPT embedding. It will also inherit nn.module, and we'll just pass. All right. Now the next thing is that we would be storing our number of layers. So number of layers is equal to number of layers, and self dot head dimension is embedding size, the integer division of embedding size by the number of heads. So basically, just a pause here. So embedding size, let's say, is 768, and the number of the heads are 2. So what we are trying to achieve in this particular thing is that we would have 2 scaled attention products. Like we would apply the attention on 2 heads, and then we will concatenate their output. So that is why we need this head dimension, which is telling us that what is the embedding dimension that is handled by 1 head. And as you increase your number of heads, then you can process all those embeddings parallelly, and then you can just like concatenate their concatenate their output, not the product. All right, so that's self head dimension. Then we need to define self, like what do these layers consist of? So they would consist of nn.module list, and it will have some stuff, right? And finally we'll have a classifier which will just give me my context length, like my sequence length, and with every sequence I will have my vocabulary. So what is the next occurred token, or what is the next occurring word in the sequence? So that is what the classifier will give me. So we can define it just here itself. So that's nn.linear, and we will go from the embedding size to my vocabulary size, right? So basically I need that my sequence, which is nothing but a vector. Now it will output some kind of a token, and the token will be within my vocabulary size. So classifier is just outputting those classes, which are nothing but the vocabularies or vocabulary size. All right, so we have defined everything. Now we can just define the forward function, and with forward we will have tokens. So the first thing that needs to be done is to define positions. Okay, so how do we define positions? So positions will be torch.arrange. So basically torch.arrange just gives you a list, or basically it gives you a tensor starting from whatever, like starting from 0 to the limit that you provide. So we are going to say that, hey, tokens dot size 1. So basically tokens or the input to this GPT is batch size cross the sequence length cross your embedding dimension. Okay, so The sequence length is nothing but how long your sequence is. So for 512, we need 512 positions. So that's what torch.arrange is doing. It will start from 0 till 512. So tokens.size, but we need to we would need to add these positions to the embeddings. So we would need to have the same dimension as the self.embedding. So let's add a dimension on squeeze at the first, like at the first dimension, we will add that. So now this will be 1 cross 512. Okay. And I'm going to repeat it for tokens dot tokens dot size 0. Like I need to repeat it. Basically I need to repeat it for batch times, right? And I need to repeat like at the first. So basically 512 will now be repeated for the batch for all the batch dimensions. So this will give me batch cross 512, and I need to move it to CUDA. Of course, the neat way would have been to just have the device, but since I'm ensuring that everything will be running on GPU, so I can safely assume that everything will be moved to CUDA. All right, so the next thing would be embeddings, and that will be self dot wait, I can just increase this. Yep, perfect. So self dot embedding, I need the tokens and I need the positions. So I will take care that in my embedding object or embedding layer, I will be passing tokens and positions both. And that particular embedding that I will get, the summation of that, I need to move this final embedding again to CUDA. All right, so now I'll just iterate over my layers. So for layer in self.layers, all right, I'll just say embeddings is equal to layer and embeddings. So it will just iterate over all the layers. I'll pass my first embedding to that layer. The output will again be embeddings, and this will just chain out, and I will get my final output. So, okay, I made a mistake on that word, so now it's fine. Once this is done, then I need to pass all this output through the classifier. So the output of the classifier will be termed as raw logits. So logits is self dot classifier, and I'll pass my embeddings. And finally, I will be passing log probabilities. So how to convert the logits to probabilities? Just apply softmax. So log probabilities will be torch not log softmax logits command dimension is equal to -1. All right, return log probabilities. Okay, so essentially what I did here is, once I have my raw logits, and at line 29, so basically at this line, when I'll run softmax, so okay, so logits dimensions were were batch size cross sequence length. So I'll just run this down. So this is batch size cross sequence length cross cross vocabulary. Now I'm running softmax over the last dimension, so over all the vocabularies, right? And as soon as I run softmax, they will be converted to probability numbers, and I will know if if I pass torch.argmax, so I will know the index of the particular vocabulary or the particular token, that which is the next occurring token, or which is the token which has the highest probability. So that is the essence of why log softmax was applied on the last dimension. And why we are applying log, because we will be writing our custom loss function. It will be same as cross entropy, but just for practice, we'll be writing cross entropy by ourselves. So okay, a quick refresher on cross entropy. So in cross entropy, we are basically passing logits and targets, and internally the cross entropy will apply the softmax, and then it will calculate the negative log likelihood. But we will scratch that away and we will do that ourselves, just for the fun of it, for the sake of exercise. So we have applied the log softmax, and now we just need to calculate the negative log likelihood. And how do we calculate the negative log likelihood? We will take these probabilities and we will multiply with the token indices, or basically with the tokens, and we would know that for which target token we have the maximum probability, and then we will just sum them up, and then we will just apply a negative. So the definition, the very definition of negative log likelihood is minus summation of log p into q, where p is your target, p is your prediction, and q is your target. So everything standard, nothing fancy. All right, so let's write the loss function. So this will take self, this will take your log probabilities now, and this will also have your target. So what we need is NLL, so negative log likelihood, and that will be equal to minus of torch dot sum. So we'll be summing something, and let's just say that we can just write that log, so log PQ, so log PQ. Now this would be log probabilities dot gather. Now remember that the target is batch size cross sequence length, nothing else. It has no notion of anything vector. So target is nothing but your sequences. So if your input, okay, so for example, I'll just quickly draw this out. So if your input looks something like, let's say it's a sequence of A comma B comma C comma D. Okay, so your target will look like B comma C comma D, and let's say it's E. All right, so basically we will have batches of these targets which are shifted by one index. So for A, the target is B, which is the next occurring token or next occurring word, and for B it is C. Similarly, for D it is E, and this just goes on and on, right? Now the log probabilities, the dimension of log probability is batch size cross sequence length, or let me just say S cross vocab. Now notice that vocabulary will have all the tokens which can be there in the target, right? Vocabulary is just like assuming that all the English alphabets is my vocabulary. So vocabulary will be 26, right? And let's say that the target is something like an 8 character long sequence. So if I say that log probabilities dot gather, and if I say that do it on the second dimension, so I'm gathering some things on the second dimension of log probability. So the second dimension is on the vocab, right? And what do I need? I need the correct targets. Targets is still so target dimension is still batch size cross sequence length. It has nothing to do with the vocabulary. It has just the sequences, right? So target, so I'll add a dimension, unsqueeze, and not at the 2, sorry, not at the 0. I need the extra dimension here. Okay, so it will be unsqueeze at 2, and I'll just make sure that this is not floating type, so I'm just adding that it should be long. Okay, so what this does is now it will have the same batch, it will have the same 3 dimensions, batch size cross sequence length cross 1. And when I say log probabilities dot gather, add the second dimension, that is at the vocabulary dimension. So for this vocabulary, for all the 26 alphabet, it will just pick out that what is this D, like pick out the target. So this vocabulary will have all the 26, but I would be just needing the probability for D, not for everything. I just need it for that particular token. So this will just broadcast all the correct log probabilities corresponding to the target token. Once this is done, I just need to divide it by target.size so that I get this log sum, like not the sum, right now it's not a sum. I would just get log probabilities across my batch, right? And then I just need the sum of it. So log PQ, and the NLL would be negative of that sum, right? So returning NLL. Now inside PyTorch, this is just handled by return nn.functional, I guess. Yeah, nn.functional dot cross entropy. Cross entropy, and now I would be just needing logits and target. So this would have been the simplest way, right? But it's just an exercise for me, so I just wanted to communicate this. All right, so I'll keep this explanation as it is. So now we have the forward function of the GPT and we have the loss function, right? So let's now move to should we write the embedding class? Let's start with the embedding class. So I'll just copy this because I need to write the init and the super, but I will copy this. Okay, now embedding was taking just 3 things, so I'll remove this. All right, I'll remove the pass. This is fine. Again, self dot vocabulary size is vocabulary size, and self dot embedding size is equal to embedding size, and so sequence length or sequence length, and I would be needing the embeddings for the tokens. So self dot token embedding will be equal to nn dot embedding, and I just need vocabulary size cross embedding size. So what does nn dot embedding do? It just it creates a lookup table which is vocabulary size cross embedding size. So imagine that we have 26 alphabets. Now we don't want to pass just these 26 numbers to the model. We want to give a rich vectorized representation of all those 26 alphabets, right? So let's say the embedding size is 768. So for each of those characters, English alphabets, we will have a 768 long vector, and that will act as an initial representation. And of course, if we don't set this, like if we don't set the learnable, or if we don't set the grad as false, then even the embeddings will be learned. Typically what happens is that we have really good embeddings. You must have heard that we have Llama 3 embeddings, we have like OpenAI embeddings. So we just take those embeddings and we set the gradients, or we set the learning as false. I will just let you know that how do we do that. But in our experiment, we will just let it free flow. We will learn the embeddings for our GPT model. We will not load any pre-trained embeddings. Okay. Of course, this will add on to the learnable parameters, but let's just see how it goes. Now, this is the token embedding. We also need the position embedding. So self.position, position embedding. It will be of the same thing. So I'll just copy this down here. All right. So that's all we need. We just need to define our three variables, the token embedding and the position embedding. And now we can just define the forward function for this. So what do we need in forward function? We would need tokens, we would need positions. So we took care of that. You see, in self.embedding at line 37, we are passing tokens as well as positions. So the positions are coming here, and they are not sent to the position embeddings yet, and even the tokens are not sent, right? So in the forward function, we will pass token embedding is equal to self.token embedding tokens. Similarly, position embedding is equal to self.position embedding positions. All right, and just to be sure, we don't want anything to do with the floating point operations right now. So this should be, oh sorry, it's not placing anywhere. We just need to ensure that this is casted to long, like it should not be of torch.float type, because everything like these are indices in the matrix, so indices cannot be float. So that's why the tokens and the positions will be of long type basically. All right, finally we would be just returning token embedding plus the position embedding. And you remember that in the attention paper, the position embeddings are interleaved addition of sine and cosine by different periods. So that gives the position that basically gives a position index which is unique to every token in the sequence. But now we are just setting this to like learnable parameter. Okay, so that is my forward function, and I will just add two sanity checks which I added I think long back in one of my assignments. So it really helps to just capture any of the inadvertent errors. So let's say that if torch.any positions become greater than equal to self.sequence length. Now this is basically saying that you want to access that particular position which is not present in your embedding, which is longer than your sequence length limit. So I don't want that. So just raise a runtime error saying that positions longer, or basically positions greater than sequence length. Okay, there's another sanity check, which is that if torch.any if tokens are anywhere greater than vocabulary size. Okay, so this means that somehow there's a mismatch between your tokenizing, or somehow there's a mismatch of initializing your vocabulary size and the tokens, right? So sometimes these kind of sanity checks really save your time. I remember that once there was there was just a simple error of not passing weight decay to Adam W, and I just wasted like around 1.5 hours just trying to figure out that why the weights are not getting populated correctly. So these kind of small sanity checks really help. Okay, so tokens not in vocab. Perfect. So our sanity check is in place, and I think we have completed our embedding. So once this is done, now the next thing is that we are going to define okay, let's see that in the GPT. Okay, so this is done, line 41 is done. Okay, so now we are going to define this, line 44. So in our module list, we would be having a notion of a transformer block. Okay, so this would be a block, and it would take some parameters we don't know right now, but we know that it would be needing head for sure, right? So the first thing that it would need is self.head dimension. It would also need so every transformer block will perform attention like the attention mechanism, and it will also perform a multi-layer perceptron. So let us arbitrarily send a 4 times embedding size for our MLP. Okay, and we would be passing, of course, the number of heads. So number of heads, and we would also be needing sequence length because we would be doing some merging and splitting of the heads in the multi-headed attention, so we would be needing sequence length as well. All right, so this is done, and now let's do that for I in range of self dot no, not self, but number of layers. So number of layers, here it is. So this is basically going to add your transformer blocks as much as you want, which will be equal to your number of layers. So if you have 4, then it will just add 4 transformer blocks, and in the end it will just have a linear classifier. So let's now define our block class, like a transformer block class. Again, it's nm.module, and let me just copy this. In these scenarios, sometimes Copilot really helps, but I've just switched that off so that it doesn't interfere with our writing. Okay, so I'm going to copy all of this, and just a second. All right, so that's head dimension. Then this is MLP hidden size. Number of heads is fine, and sequence length is fine. Then super block self, this is also fine. Then self dot again head dimension is equal to head dimension. Then self dot I'll just copy paste everything here, is equal to MLP hidden this. Self dot number of heads is equal to number of heads, and self dot sequence length is equal to sequence length. Okay, removing commas. Perfect. Now we have the notion of head dimension, and we also have the notion of number of heads, right? Now the total embedding size, which is self dot hidden size, actually, now hidden size, that is actually the multiplication of number of heads into head dimension, right? So you see the head dimensions were divided. So how did we obtain head dimension? We divided the embedding size by the number of heads, right? And then we passed on head dimension separately and number of heads separately. So we need to reconstruct this embedding size. So basically the hidden size is nothing but the embedding size, right? Okay, so what does this transformer block needs? The first thing is attention. So self dot attention, and we would be making a multi-headed attention. So let us just call it as let us just call it as MHA, multi-headed attention. And this would need again head dimension, number of heads, and it would need the sequence length, right? Now once I have the attention thing done, then I would be needing layer norm. So self dot layer norm 1. So what does layer norm do is, so there's a great paper, I think, I don't remember, I think the paper is about group normalization. So it has a great visualization of different normalizations that are happening. So there's this cuboid figure which basically shows that if you have channels on your x-axis and if you have your batch on your y-axis, and then the z-axis are just the image dimensions, then basically layer norm is calculating the batch statistic. So it's calculating the average statistics for every sample in the batch across all the channels, right? So that is layer norm. And group norm is it's just a refresher for anyone who's interested. So basically group norm is one of the cases between layer norm and instance norm. So so group norm is in between the two ends of the spectrum, and two ends are the instance norm, which is calculating the average statistics for every sample per every channel. Oh, we should not say per every, but for every sample and every channel. And the layer norm is doing for every sample across all the channels, and group norm is dividing the channels into groups, into small groups like 2, 3, whatever the hyperparameter is. The batch norm is a little different. The batch norm is calculating the batch statistics. It's calculating the statistics across the batch and the channels. Not across the channels, across the batch. Okay, for every channel. So that is the difference. But I would recommend to read that group normalization paper. That's a beauty. And you'll find a lot of Medium articles on differentiating the group norm versus layer norm, etc., etc. So just a cool fun fact I observed in one of the experiments I was doing. Group norm really works best with ResNet models training on ImageNet, but layer norm does better on language models. So this is like an empirical observations. This is like an empirical observation that we have in our couple of experiments in our latest project. So okay, coming back. So layer norm 1. So this will be a layer norm. We would define this custom layer norm ourselves. So we won't take the PyTorch layer norm. So all I need is just self.hidden size. And why hidden size? Because now I would need the full dimension, because I need to calculate the normalization statistics across one sample, but across all the channels, so across the whole dimension, right? So that is why I need I need this hidden size, which is the multiplication of the number of heads and the head dimension. All right, so I need this. Then I would be needing my MLP. This would be just my nn.sequential. Oh, it doesn't. I thought that VS Code just completes torch primitives. But anyways, okay, nn.linear and self.hidden size, self.mlp hidden size, right? And nn.sequential. Okay. Then I would be needing nn.gelu. So this is a slight difference. Usually we use relu, but in the GPT-1 construction, we are not using the relu function. We are using gelu, and the difference between them is that if you have any number that is less than 0, so you just have a flat 0 as an output, and then you have just whatever the number. So basically relu is like max of 0 comma x, but gelu is a little different. Gelu has a small graph within the range of zeros, and that is negative. So it has some values near the neighborhood of 0, and then as your value approaches large negative numbers, it goes on to 0, like it approaches 0. So gelu is an interesting function, and an interesting property of gelu is that it is not a one-to-one function. So basically it has a kind of a bend. So for 2x values, you have the same y value. So that's an interesting property of that. But that doesn't hamper its differentiability, so we are good to go. Okay, coming back. So nn.gelu, then nn.linear again. So now we have we have increased our latent representation. Like MLP hidden size is 4 times of the hidden size, so now we are constructing it back to the same hidden size. So self.hidden size. All right, so I think that's it. We won't be needing anything else. So MLP is done. Then sorry, after the MLP we would be needing another layer norm, and that would be again layer norm self.hidden size. All right, so we have the blocks ready, so we will just quickly define the dummy classes, which we will complete later on. Class nn.module pass, and okay, so MHA is done, and then we would be needing layer norm. Oh, that's it. Okay, so how do we define the forward function now? Let's see. So def forward, we would be passing an input, and the first thing that we need okay, so now we have entered our transformer block. So the first thing that will happen is we will pass this x to our attention layer, right? So we would say that attention output is self.attention layer. Once it has done, then the same thing, like you see, we have defined all our blocks in a sequential way, and we just now need to pass our input through these sequential layers without any confusion. So first the attention, then the attention to the layer norm, then the output to the MLP, and finally through the layer norm. So we already passed through the attention layer, then so attention output is equal to self.layer norm 1, and we would add x plus attention output. So x plus attention output is nothing but a residual connection. So we have the input, we pass on through the attention, we will add them together, and then we'll pass it through the layer norm. So this increases the activity between the x and the attention output, right? So just giving us more richer representation. And actually this is a good food for thought. I didn't investigate why this is necessary, so I will surely look it up, investigate more. Okay. All right. Now we need MLP output. So that will be self.mlp attention output. And finally, we would be needing output from our self.layer_norm2. And now we'll not be passing input, like we'll not be passing X with the MLP output, but we'll be passing on the attention output and the MLP output. So basically, in the layer norm, we are passing the current layer and the previous layer. So in the layer norm 1, we are passing X, which is the previous input, and the attention output. And then in the layer norm 2, we are passing the attention output and the MLP output. So MLP output is the current one and attention output is the previous one. And finally, return output. That's it. So this block, like this completes our transformer block. So I think this is pretty modular how we are trying to approach everything. So I think this design really helps, that you first define your global structure, you define all the essential blocks that are required, and then you keep on going iteratively or recursively inside each block and just define all the things that are needed. And since I've already done this a couple of times, so everything is going very seamlessly. But if anyone is trying to do from scratch and without any help, so it would be like you would go inside a module, you'll find out that, oh, I need these kind of variables, and I'll just define them in the outer class and then just try to capture them and try to use them inside the inside the nested block or inside the component that is required. Okay, cool. So the block is done. Now let's move to the most important heart and soul of transformer, which is the multi-headed attention. All right, so again, I would be needing these kind of things. So let me just copy this down. Okay, MHA just need the head dimension, number of head, and the sequence length. So I'll just remove this. So it needs head dimension, number of heads, and the sequence length. Perfect. The name should be MHA. Okay. Head dimension is head dimension. Now we don't need MLP, so delete this. Number of heads, that's fine. Sequence length, that's fine. We don't need hidden size right now. We'll see how do we recombine. So basically here also we'll be using the multiplication between the self.head dimension and the number of heads, right, to construct the whole embedding dimension. Now the multi-headed attention, or basically any attention block, it uses queries, keys, and value matrices. So let us first define those QKV matrices. So self.query weights, I'm referring matrices for weights. So query matrices means query weights. Okay, so this would be a simple NN, this is nothing but a linear projection of our total embedding size to total embedding size. So we would just say self.number of heads multiplied by self.head dimension, and this would be repeated. Oh, sorry. Okay, I'll quickly explain why did we do this. So query is done, then keys, and then value. Okay, so basically we have a query matrix. It is similar to an embedding. Embedding is nothing but a linear projection, right? It's a lookup table. So query weights are also like that, but they are of equal input and output dimensions. So basically we are having embedded size, cross embedded size weight matrix, or the weights are of equal input and output. So we are projecting across the same dimension. Okay. Now, apart from this, we need another weight matrix, which is the output. So that's called as WY, or let's call it WO. And that's also the same thing, a linear. So this will be used to multiply. So as you might have guessed, that the query weights are used to multiply, so basically query weights are multiplied with the query, key weights are multiplied with the key, value weights multiplied with the value, and the weight output will be multiplied with the attention output. Okay. So these are the things that need to be defined. That's it. Now we can move to how should we say, apply attention. That's the main function that is there. So it will have query, not query. It will be queries, because it's a batch of queries, keys and values, right? All right. So now we have to pay a little bit attention. We'll have to pay a little bit attention to this function. We'll have to focus, and we don't want to make mistakes here. Okay. So the first thing is the attention score. Okay. Let's just call it that, attention. And that is nothing but torch.matmul queries, and keys have to be transposed, but the transposition, like the transpose, has to be done such that the last column comes at the second last and the second last goes to the last, right? So this will be keys dot transpose -2 and -1. So this will just flip, like not flip. I think the better word for transpose is permute. So it's basically the permutation of the axis. Now we have to be very careful that we should not use view, like we should not use keys.view and then inside view we just adjust like inside view, if we adjust the dimensions, then it will just rearrange the data according to the shape that you give to it. But that is not equal to changing of the columns or changing of the axis. So we never use view for transpose for permute. Okay, so we have to be very careful of that. I made this mistake in my assignment, so that's why I'm stressing this out. Okay, so keys or transpose. Now okay, attention, this is done. Then we don't okay, so I'll leave a little space over here, and after the attention I would just want to just a second. Okay, so I would just want to divide my attention by the self.head dimension, right? And so basically we're just scaling by the head dimension, and the reason is that if we don't do that, then our gradients will quickly saturate as soon as we apply the softmax. So applying softmax, the variance will kind of increase and the gradients will saturate pretty quickly. But if we are dividing by under root of head dimension, then the variance is preserved and our gradients don't saturate pretty quickly. So that's the essence of dividing, or basically scaling by the head dimension. And it's not just a simple division, it's like square root. So 0.5. Okay, once this is done, now we need to apply the softmax over the last dimension. And I think it would be better if I just explain that what are the dimensions of queries. So query looks like batch size cross sequence length cross the embedding. Okay, so it looks something like 16 cross sequence length can be 10, and the embedding can be like 512, right? So this is what the dimension of query, key, and value looks like. Okay, so when we want to multiply query and key, so basically we would have the same dimension for the keys as well. So so this was for query and this was for keys, right? Now if you apply the transpose, so basically 512 would come inside and this will become 512, and I'm just adding dot transpose. So basically as soon as you have the transpose of the key, then your 512 or the embedding dimension would come inside. And now if you multiply query and key, now because they are multiplicative, now basically they are eligible for multiplication. So now if you multiply them, so their output or the attention output looks something like 16 cross 10 cross 10. So basically it is giving for every query and every key a score. Basically this is nothing but a score, right? And we want to convert these scores into probability numbers. So how do we do that? Just by applying softmax. So attention is equal to torch dot soft. Oh no, we don't need log, we just need softmax, and attention, and the dimension should be -1. So basically we need the log probabilities across the last dimension, right? Like for every query we need the log probabilities for all the keys, or not log probability, sorry, the probabilities for all the keys, right? Now once this is done, we have to again understand this is still attention at one head, right? So we need to merge all these heads together. Okay, so how do we do that? We would just say return self dot, we would say a merge function, merge heads function, and we would multiply torch.matmul our attention and our values, right? So once we have the log probabilities, we will just multiply it by values and we would just merge them together. And why merging? So we don't see any number of heads right here in the dimensions, but I'll just explain how this merge heads come into picture. Okay, so I left some space here, which I'll again come back. So our function is not over yet. So let me now define the forward function first, and that will make things clear. So def forward self.x, and okay, so now I need queries. So now my x is basically batch size cross sequence length cross the total embedding size, right? And I don't want to compute my matrix multiplication on the complete embedding size. I want to just divide it by my number of heads, compute everything parallelly, and then concatenate the output. So I need a function that splits my query keys and values, right? And I'll explain that what does splitting means. So it will split heads, and I'll pass my query weight, I'll pass my x on this, right? And I will do the same thing for my keys and values as well. So keys and values, query K, query V. All right, so once this is done, then we would have concatenated values, which will be self dot apply attention. So basically self dot apply attention is this function. We have the splitted query keys and values. It will do its job, and then finally it will merge the heads and it will return the final value. So queries, keys and values. All right, and finally the output would be self dot wo, and we would pass on our concatenated values. Okay, and then return output. All right, so now we need to introduce split heads and merge heads. So let me quickly do that, and then I'll explain what are the dimensions that are coming into the apply attention function. So self dot split heads. Now this is also a very important function, so please be careful on that. Okay. Oh, sorry. Def split heads self x. Okay. Now notice the dimensions. It will be batch size, sequence length, and the embedding, which I don't care right now. Okay. Now I'll be using my view, but notice how carefully I'm using. So I'll reshape how. I'll just tell you x.view. So I need batch size, sequence length, now number of heads, so self dot number of heads, and -1. So basically what it does is okay, so let me explain here. So imagine that your x is this, right? So as soon as you say that you need to view your x as batch size cross sequence length cross self dot number of heads, so it will instantly do this, and let's say that the number of heads is 4. So now it will automatically calculate the last dimension, and it will give you this. So now the rearrangement is still on the last dimension. It has just split it into 4 groups or 4 heads. So we are still okay. We are still safe to use the view function, right? Because we haven't changed the axis. We are still on the last dimension. But now we need to change the dimension, right? So how would we do that? So basically we would say that x dot permute, and the permutation should be 0, should be same. Now at the first you should have the second. So basically the number of heads will now come at the first dimension, and the sequence length will go afterwards, and the rest of it remains as it is. So now this will get changed into something like this. So 4 cross 10 cross 128. So now your heads have come in the beginning, and now you have sequence length cross 128, and now all your attention will be applied on this 10 cross 128, which is a smaller matrix. Okay, so can you see on this 10 cross 512 we were applying our apply attention function on the whole, but if we just change this, then our results remain the same, right? So it's just that the apply attention function is now working on a smaller matrix. just 10 cross 128. Okay, we did all that, and now towards the end we need merge function, which is exactly opposite to split heads. So we would just copy this function and we would just write merge heads. So again, towards the end it will have something, but the first step now would be to permute it back, right? So we would just permute it back. So now this was appearing to be like that. Oh, just a second. So in the merge, okay, yeah. So in the merge, we are getting the tensor which looks like 4 cross 10 cross 128. And now we want to again give it out in the form of batch size cross sequence length cross the entire embedding dimension. So what do we need to do first? We can't just simply do a view and then we just arrange our dimensions. That will just give us incorrect tensor. It will be of the correct shape, but how the data will be arranged, that will be destroyed. Okay, so we need to permute it first, or we need to flip the axis. That is the step at line 55. And once this is done, then finally we'll just multiply it by self.head dimension, right? So this will give me back the merged head. So now this will be just giving me 512 again. So this is very essential to understand. If you didn't get it first time, rewind this portion and try to watch it again. Return x. Oh, I forgot the return statement here. Return x. Okay, so my split head is done, my merge heads is done, right? So I can collapse them. My apply attention is also done, but I left some space here, right? So let me come back. Okay, so we have applied attention on query keys and values, but we forgot to take care of the causal relationships between the tokens. So query at first index cannot look at an index that is greater than 1. It can only look at an index that is previous, like that is lesser than it, because a word cannot look into future. It can only look at the words that are behind it. So we need to apply that causality, and we can do that it's pretty simple. We can just apply a sequence mask. So I already have written it. So basically a sequence mask is nothing but an upper triangular matrix of all ones, and it will be of the appropriate dimension of queries and the keys. Since our queries and the keys are of the same size, so this would be just a square matrix, and we just need to fill upper triangle as 1 and the diagonal as 1 as well. Oh, sorry, where did it go? Yeah, here it is. Okay, once this is done, then my attention has to be masked fill with sequence mask, and wherever it's 0, I will just put a huge number which is infinity. Oh, minus infinity, not infinity. Just be careful, it's not infinity. You need to put it a very huge negative number, because you don't want it to get accounted in the probabilities. So basically in the softmax, it will be e raised to the power minus of x, right? And if x is a negative number, then it will just give out negative infinity. Okay, all right, so this is fine. Now I can collapse all the spaces. All right, so my attention function is done, merge heads is fine, forward function is also done. Cool, so my MHA block is done as well. And now the last part that remains is the layer norm. All right, so layer norm is pretty simple. It won't take a lot of the time. I just need this def init layer norm. Okay, I was thinking that this video would become shorter, like approximately 1 hour, but I think 1 hour is already up. So I think I'll split it into 2 parts. Let me complete the model architecture for like once and for all. So in the layer norm, I would need the hidden size. That's it. Like I just need my hidden size and some kind of small epsilon value. So epsilon value should be like 1e minus 5. Then I would be needing self dot hidden size is equal to hidden size, and then self dot epsilon value. So you don't need, like, we don't need to compute layer norm manually, but since we are coding everything from scratch, so it's like all the components are like just written scratch from the bottom. Okay, self dot weight, it will be an nn dot parameter. It's not a layer, either it can be a parameter or maybe a buffer. Oh no, it cannot be a buffer, sorry, because it's not shared. So torch dot tensor and of the hidden size, right? Self dot bias is again the same thing. Hidden size, yep. Self dot like basically resetting the patterns. So at the call of layer norm, the parameters will be reinitialized, and the forward function will now take care of it. Self dot input. So we'll first calculate the mean, which is nothing but input dot mean at the first dimension, which is the batch size cross sequence length. So sequence length is my channel, and I need for the sequence length, and it will be keep dimension at true. Then I need the variance, and it will be, I'll just talk that how variance will be computed. So it will be input dot var and dimension at -1. Oh, sorry. No, layer norm batch size cross sequence length cross your embedding. So it's not at sequence length, but it's at the embedding. So the layer norm would also have the mean for the -1, not 1. Sorry, not for the sequence. We don't need to calculate the mean for the sequence length. We need the mean for the embeddings, like for the embedding dimension. So that's why a -1. Now we need var, but we need unbiased as false. So we don't need Basel's correction. So you know that when we want to calculate the sample mean, we use a Basel's correction, which is nothing but including the denominator with n-1. But we don't need that. We need just the batch estimate, or we just need the sample estimate. So we need the denominator to have n as it is. That is why the unbiased is false. We don't need the unbiased one. So we need the biased one, that is n. Okay. So unbiased is false, and again keep the dimension. Oh, sorry. Keep dimension as true, and then outputs is equal to input minus variance. So this, input, sorry, and outputs is equal to outputs into self dot weight plus self dot bias, a simple linear multiplication, just to return outputs. Perfect. Now once it's initialized, so resetting the parameters, like it's just happening once, so we need nn dot init, I think it's zeros, no sorry, we need ones for self dot weight, and we need the biases to be 0, so zeros, oh sorry, I guess this is underscore, so resetting the parameters must have self. Okay, so self dot bias. All right, our layer norm is also done. So collapsing this. All right, so this is how our architecture looks like. We have the GB, so first we define, so if we go from bottom to top, we first define the GPT class, which utilizes GPT embeddings, and it utilizes the block or the transformer block, right? We pass on our tokens through position embeddings and the regular embeddings. We add those embeddings together, and then we pass on these embeddings to our transformer block. Once it is passed from this transformer block, it is passed through the classifier, and then we just get our log softmax, which is our log probabilities, and the loss function is simply the cross entropy loss. Now GPT was using the embedding class as well as the block class. So then we define the block class, and inside the block we have attention layers, we had the layer norm, and we had the MLP block, and then we just sequentially passed on everything from attention to layer norm, then to MLP. Then we defined our layer norm class, which is pretty simple. I won't go it again. And then we notice the heart and soul of our transformer block, which is the multi-headed attention. We noticed that inside the forward function, we first passed our input through a linear projection into the embedding space, and we passed those query weights, not the query weights, but that whole query matrix, through our split heads. So basically, we had batch size cross sequence length cross the complete embedding dimension, which for example is 512. So split heads will split that embedding into number of heads cross the embedding dimension per head. So we will have 4 cross 128, and we split that. We permuted inside the split function, we permuted the number of heads to come before, and then we had the sequence length cross small embedding dimension per head. So it is like 10 cross 128. Now once we have our queries, keys, and values, we pass those values through our apply attention function, which is this, and we saw that this is the typical mathematical implementation of attention, which is multiplying the queries and the keys transposed, then just multiplying them by a mask so that the tokens don't communicate between the future tokens, and then scaling the attention through the head dimension or the embedding dimension per head, then applying a softmax over the embeddings or over the attention over the last dimension of the attention scores. And once I have this, then I can just concatenate my output, which is done through merge heads. And of course, there was a matrix multiplication between the attention and the values, completing the mathematical implementation of attention. Okay. So it seems to be convoluted, But if you break this down into sequential layers or sequential functions, then it's like a cakewalk. And finally, we looked into GPT embeddings, where we have token embeddings and position embeddings, and we are just adding them together. We had our sanity checks, which were simple enough, and we are keeping these embeddings learnable. So we are not using pre-trained embeddings. All right. So this completes our model architecture. Now I'll pause the video here because it's already 1 hour 20 minutes. And in the next video, I'll continue with writing my my data primitives and then continue training this model on Wikipedia dataset. So stay tuned for part 2. Thanks.